The third sub-process in Unit 6 is sequence activities. And here we're going to build a network diagram, which is going to show the time relationship of all the activities of all the work breakdown structure components that we've defined. So now we've got basically an input here, the scope management plan coming in, the activity list and attributes, the milestone list, project scope statement, and the corresponding environmental, enterprise environmental factors and organizational process assets. And we're going to talk about how we construct a precedence diagram and how we handle dependency and how we handle leaks and lags. And finally, we're going to get basically a schedule network diagrams out here or a visual description of how we're going to run the project. Now, in terms of scheduling, there are 3 or 4 different ways we can take a look at scheduling. One is that we can use the Gantt chart, which I'm sure you're all familiar with, which basically shows a bar chart and the relationship of certain activities and how far we've gone in each activity and how those bars are connected together. We can do milestone charts. Milestones basically show us the timelines when certain milestones are going to be done. And then we can do network diagrams, such as an arrow diagramming method or precedence or PERT chart, that basically show you in time how all the little activities are all linked up together. Now, there is no perfect way of showing a graph. Each of the 3 different techniques we just mentioned has some advantages and disadvantages. Gantt charts don't show interdependencies very well. PERT charts, etc., are very time intensive and tend to have too much detail. Milestone charts tend not to have much detail at all. Now, each is useful in its own right, and we will use one of the 3 approaches depending on our audience and our stakeholder tolerance for detail or lack of detail. And in fact, in any good project management tool like Microsoft Project, you can ask for a Gantt or a PERT or a milestone chart at any time. So for example, suppose we had a very simple project here that consists of 7 nodes here. We can see that we've actually got the Gantt charts laid out here of 1 and 2 being done, then 3, 4, and 5, and then 6 and 7. We have milestone charts here, the milestones being created at each one of these major activities. And then we have a PERT chart here, which tells us how long each activity is going to take before we can go to a downstream activity. Each shows a little bit different viewpoint of how we view the actual project itself. Now, when we talk about constructing a network diagram, we need to realize we're constructing a diagram or a visualization of all the activities of the project. So we need to know what the activity interdependence is. We want to be able to compute the project completion time. And for any given activity, what happens if we start early on that activity? Can we postpone it and start late? We can try and do trade-off analyses that, well, what if we take this particular path and try and get that started faster? What's going to be the effect on the total schedule and cost? We can do what-if scenarios. We can do crashing if we want the project done before a certain time. How can we speed up the project itself? If we've got slippages in planning or in performance, can we improve upon that? And the network is going to give us a method for doing performance evaluation of the project in general. The tools and techniques, this is probably the most complicated set of tools and techniques in the entire course. And we're going to start off by talking about precedence diagramming methods, or PDMs, and then talk about dependency determination and leads and lag. Now, the precedence diagramming method is also called an activity on node, where basically the effort is on the node of the activity, and then the arrow points down to the dependency of downstream activities on the completion of the activity of that node. And in fact, PDMs are probably the most common used. And so here we've got an example here where we begin the project here at that box, begin, we end the project down here, and we've got a whole bunch of work breakdown structure components here that we're executing, and here's the relationship between them. And we could flesh that out by putting time estimates in it and computed time to complete that diagram. Now, for the activity on the node, the event is the start or end of a set of activities, which basically has a circle associated with it. And in that circle, we've got basically an identifier saying this is activity 6, and this is the length of time to do it. So in this particular case, we would interpret this as being activity 6, which is complete the testing, will take 2 time units to complete. When we get that done, we can then prepare the final report because now all our testing is finished. That is ID activity 9, and it's going to take 3 time units to complete that. Now, when we start putting dependencies together, we need to take a look at the dependency relationships. Let's go back to the previous example here. The implication here is that before we can start activity 9, we have to complete activity 6. So this means that this is basically a finish to start relationship. And the finish to start relationship says you've got to finish this node before you can start the next one downstream. And this is by far the most common. But we can also have 3 other variations of this too. We can have a finish to finish relationship. We have to finish this particular activity before some other activity can finish. So there's an interesting example. And we can have a start-to-start relationship. We must start this activity before the next activity can start. And finally, we can have a start-to-finish. We have to start this activity before the next downstream element can finish. Now notice when we specify F to S or F to F or S to S or S to F, we're assuming 100% completion of each activity. Now that's just an assumption that we're making. We could have easily have said we'll allow for 50% too. But generally speaking, it's simpler to demand 100% completion of the activity. So with a PDF analysis here, the network analysis is going to look like this. We're going to have a description of the activity itself. Then we're going to have an activity number down here and a duration, and again, we're going to assume, let's say, weeks for completion, but some convenient time unit that's consistent for the entire document. Then these little ears up here are going to have the earliest start and the earliest finish that we can have for this activity. As we'll see, on certain activities that can vary. Down here, we're going to have the latest start and the latest finish before we're going to compromise the actual activity itself. Now, when we start naming our days, and suppose our time unit now is in days and not weeks, do we start with day 0 or day 1? So, for example, we could start this activity A here by saying it takes 4 activities, days to actually do this. We're going to start at the beginning of day 1, and we're going to complete at the end of day 4, so that's 4 activities. So then the downstream B here would begin on day 5, in the morning of day 5, and end in the afternoon on day 7. But we could have equally as said, let's call this day 0, meaning we're not going to start this thing until that 0 clicks over onto a 1, and then it will actually proceed until we finish. And similarly, activity B here starts at day 4, which means that when we really start, we increment that to 1 to start at day 5 to actually complete. Doesn't matter which way you do it. In fact, lots of times people start at day 0 just for convenience. So for example, here I'm starting at day 0. It takes me a day to do this. Day 1, it takes me 3 units to do this, and so on until it takes days 2, 3, 4 to complete this, days 5, 6, 7, 8, 9 to complete this until we finish at the back end down here. And you can see by the end of day 12 that we've actually finished this. Now, what we've done in doing this is what we call a forward path. So we take a look at all the times to do each one of these units. You can see intuitively that this path from A to B to D to F is in fact the longest path through that particular unit. It's going to basically take me 12 days to get down here at that particular time. And you can also see that we've got the earliest start and the earliest finish at here down here. We haven't done the latest start and the latest finish. We could have started at the back end, at F, for example, and gone back and filled in these subunits down here, latest start and latest finish, until we got the thing completed. Now, in doing a backward pass, if we have the completion date specified and carved in stone, then we start at the back end and progress towards the beginning end to see, can we get that thing done if we actually do that? And if we turn out to get a negative value, it means that we've waited too late to start the project, we can't finish. Of course, the forward pass and the backward pass should give the same result. The critical path is the path where basically there is no slippage of any time units. In other words, it's going to take me 12 days to complete this project. These activities here are on the critical path. If any of those are delayed, that project is going to be delayed. And you can tell by saying the earliest start and the earliest finish are the same as the latest start and the latest finish here. These guys are identical all the way through. Now, if we take this unit down here, we can start this unit. The earliest start is at day 1. The earliest finish is day 3. But the latest start is day 2. We could delay this for day 2 because it's only going to take 2 units to do this. If we delay for day 2 and do nothing, sit around the water cooler, then both these guys will now be on the critical path because we've got 2 days to get to activity D at that particular point there. Now, this activity, critical path activity, is extremely important. Anything on the critical path we have to monitor very carefully because any slip on the critical path means a slip on the total project. Okay, so the idea of a critical path then is that path of important events where if there's any slippage on that path, the entire project is going to be delayed. The forward pass is done to estimate the finish date. The backward pass is done when the finish date is fixed, and you want to know by what point do you have to start. Now we can expand this out in great detail. Here's a much more complicated diagram with all the units filled in, and you can see we started here at the back hand end here and done a backward pass, and in doing the backward pass it turns out we've ended up with a negative value here, which means that we cannot meet that completion date by starting now. We should have started 8 days ago. Now the second activity type of diagram is activity on the arrow and not the activity on the node. This actually was the first type of diagram to be done, and these are often called PERT diagrams. Here we've got activity 6, which is complete testing, and then it's going to take 2 weeks before we can start activity 9, which is write the final report. So the activity here is on the arrow and not on the node. And so with arrow diagramming methods, here activity on arrows, then we can have what's called burst points and sync points. And you see here is a burst point here, where now we can start 3 downstream activities at the same time. And here we have to wait until 3 activities are completed before we can progress to our sync point. And again, we can have the idea of a critical path. PERT diagrams try to introduce some variation. And in fact, rather than have just always discrete values, they say, well, we know we're going to have some variations in our estimates. We say we're going to do it in 6 days, but that may be 8 days, or maybe we get lucky, it can be done in 4 days. Activity on arrow allow us to use the rule of 6, which basically says, what is the expected value of that particular activity? What is the most optimistic? And what is the most pessimistic? Then we add together the optimistic estimate plus 4 times the expected or normal plus the pessimistic and divide it by 6 to get us a more realistic value itself. And as we'll see, we can do this if we've got a high variance in our scheduling activity. And in fact, when we do this, the opposite of the PERT diagram, which gives us a high variance approach, is the critical path method, which doesn't allow for any variance at all, but assumes we know exactly what we're doing. Now we can do this with the critical path method, where we just use the actual critical path and concentrate on that. There is a technique called GERT, the Graphical Evaluation and Review Technique, which basically allows us to do loops. In fact, when you see the examples that we've done let's just do a couple of examples down here. There, like a diagram like this. With a diagram like this, there are no loops in that diagram. You've got to do things exactly as you said you were going to do them. But the reality of life is that when we're actually progressing through, we may miss a sign-off opportunity. We didn't do the work correctly. We've got to go back and do a recorrection. So what GERT does is permits us to have loops and go back and redo things. And you can imagine it's going to make technique much more complicated. All we're going to talk about now is that GERT can be used to allow looping in the techniques. The critical path method or the activity on node or the activity on arrow do not. Okay, so let's take a look at the PERT network analysis in more detail, and we're going to finish off by talking about how we can crash. And we talked about that before. The PERT basically uses a weighted average, such as the rule of 6. It can also, here's the rule of 6 basically spelled out. The best case example, the most likely case, and the worst case example, all of these divided by 6 to give us an estimate. And what we're basically doing here is coming up with basically the best case estimate and the worst case estimate and the expected value here, and the most likely. That tends to follow what we call a beta distribution. If you look at a beta distribution, it's much wider on the right-hand side than it is on the left-hand side. So, for example, if I'm going to try and give you an answer to the question, how long does it take me to drive to work? My most likely value is 30 minutes. So on average, I'm going to take 30 minutes to drive from my house to the university. The best case example would be on Sunday morning when nobody's on the highway and I'm taking the 401 and I cheat by speeding a bit. I can shrink that sucker down to, let's say, 20 minutes. But I can't do any better than 20 minutes. No matter how fast I go, my car just will not go that fast. But on the right-hand side, the worst case here could be far worse than 30 minutes. If you think of a giant snowstorm in February with sleet and freezing rain and hail and crap and corruption, and then a big accident that shuts the 401 down, it could take me 5 hours to get to work. So this is stretched out far, far to the right. And what we're basically saying is that the expected value is going to be shifted to expect that shift to the right. And so this is just basically a 3-point estimation. This is a beta distribution where we can actually use the distribution to automatically generate times which, if we plotted them, would follow this graph. In estimating the standard deviation in PERTs, we can make a crude estimation by taking the worst case estimate minus the best case estimate and divide that by 6. So in other words, in the worst case estimate I just gave you, basically the worst case was, what did we say, 5 hours? So that's 300 minutes minus the best case, which is 20. So 300 minus 20 divided by 6 would give you an estimate of the standard deviation, which is huge. If you've got more than one activity, you have to add the variances, which, if you remember from stats, is the square of the standard deviation. So you have to add the square of these. So for example, suppose I wanted to compute the actual standard deviation of completing the path A through D. And to complete path A here, my best case is 2, my worst case is 4, my expected is 3. To pass from B to C, my most likely is 7. From C to D, my most likely is 5. So if I compute the actual standard deviation on this particular path here, my estimate is going to be 4 minus 2 divided by 6, which is going to be 2 over 6, or 1/3. My estimate of the standard deviation from B going to C is going to be 10 minus 4 divided by 6, which is 1. And similarly, my estimate from C to D is going to be 7 minus 3, which is 4 divided by 6, or 2/3. So those are the 3 standard deviations. If I want the entire standard deviation from A through D, I add up the squares of the 3 that I just computed. .33 squared, 1 squared, .67 squared, and take the square root of the whole bunch of them, and I come up with a standard deviation of 1.25. So that enables me to make an estimate here my actual expected standard deviation is going to be basically the average of the likely one, but the standard deviation is going to be 1.25. I need to talk about dependencies too. Certain activities demand that other activities have to be done first. A hard dependency means you must complete one activity before you can start the next downstream activity. A soft dependency means you may not be able to have to actually complete the entire project. So for example, if I had a high-level design followed behind requirements, then a soft dependency would mean I can get some of the requirements done, and when I get those fixed, as long as the rest of the requirements don't depend on the initial set, I can start the high-level design based on those requirements already being done. And finally, there are going to be external dependencies which are going to be imposed, which are beyond the project manager's control, and we need to know those. So for example, Y2K, the great effort to get everything done before we roll over into the new millennium, was an example of an external dependency which is beyond the project manager's control and could not be avoided. Sometimes in PERT diagrams, we need to insert dummy variables or activities. These are activities that don't take any time, but enable us to actually make sure the sequencing is done. So in this particular case here, we have a restriction that 1, 2, and 3 must be completed before we can start 4. So in that case here, we would draw in a dummy activity here between 3 and 2 that took 0 time, just to make sure that these guys are all completed before we transition over to activity 4 at this point. Now the slack time is an important variable. It's basically the difference between the scheduled completion date and the required date to meet the critical path. So if we take a look at TE to be the earliest time when an event can take place, and TL is the latest time an event can take place, then the slack time for that would be the earliest time minus the latest time, the absolute value of that difference. Now, if it's on the critical path, then the earliest time and the latest time an event can take place is exactly the same. So the slack for anything on the critical path is 0. Now here we've got an example of a PERT diagram here with a bunch of activities that we've defined. So let's take activity 1. Its earliest time start and its latest time start would be 0 until we get started. Now if I take 3 units to get to here, then the earliest time start for 2 and the latest time start for 2 is going to be 3. Similarly down here, the earliest and latest start is going to be 10, and finally the latest and earliest start here to get to the end is going to be 15. Now if we take a look at activity 3 here, the earliest start here is going to be 2, because I can start that immediately after I've got 2 units done. I can begin this. Now I can also delay that till time 5, because it's only going to take me 5 time units to get through to here. I've got 10 time units to get through to here on the critical path. I've only got 7 time units down here. So now I've got a slack of 3, because the difference between these two is now an absolute value of 3 time units. So I've got a slack of 3 that I can delay activity 3 for 3 time units before it goes on the critical path. After 3 time units, if I haven't started by this time here, I have put this as the critical path, and I just delayed the project. So we can expand that even further as we did with the activity on node, with the earliest start and the earliest finish, latest start and latest finish. And in a PERT diagram, we can do that, for example, by having the activity identification, earliest start, earliest finish, latest start and latest finish, and the activity time. So we can do exactly the same thing as we did before. And there's an example of a PERT chart with full slack times built in, and we could actually go through and compute the critical path for that particular diagram. Now, when we're PERTing along, we're basically going to do something like this. We're going to develop a schedule. Then we're going to take a look at our schedule and say, well, is the cost appropriate? No. Then go back and change the schedule until we make it appropriate. Is the cost acceptable? Then is the time limit appropriate? No. Go back and rejig the diagram until we get that in place too. And that may affect the cost, so we may have another feedback loop here until we get both the time and the cost acceptable. Then are the resources appropriate? And if we got enough resources to do it, otherwise we've got to go back and reset the project plan to take that into effect. And then finally, can management approve the plan we've come up with? In other words, we say we've got the cost and the time and the resources allocated appropriately. Does the organization agree? And if they do, we finally baseline the plan and the schedule. Now we're into business. Now, how do we feedback? On the right-hand side, we just magically said we do something to fix it. Well, we could transfer resources from the non-critical path, or the slack path, if you like, to the critical path. In other words, resources that are on non-critical path activities, on slack paths, we can transfer over to critical paths. Now, we're making a huge assumption. This is one that the PERT diagrams make, and that is that resources can be arbitrarily shifted from activity to activity. Now, in highly technical areas, that simply is not true. And that's why the activity on node is more accurate for complicated things like engineering. PERT diagrams assume that we can move resources around willy-nilly, or if you like, that every resource is capable of doing every activity. And in certain cases like construction, that may be true, but in a highly complicated technical area, it certainly is not. Second thing we can do is we can eliminate activities, and we have to be very careful in eliminating activities. One of the knee-jerk reactions of the pointy-haired boss when the schedule starts to get tight is cut out testing. We don't have time to testing. We've got a schedule to meet here. Cold weather, who cares about cold weather? I've got a schedule to keep. Launch the rocket. But the O-rings may fracture. I don't care. I've got a schedule to keep. Launch the rocket. You want to be very careful about eliminating activities that you don't throw the baby out with the bathwater. We can always add more resources. That's true. That's going to drive up the cost. Is that okay? We can try less time-consuming activities, and again, that has to be consistent with quality. If we need to shorten the time, if we've got the resources, we can parallelize the work activity. We'll talk about that. We can try to shorten the critical path, or in other words, crash the critical path, and we'll talk about that in a moment. And we can try and shorten the earliest activities to get started sooner. We can try and shorten the latest activities. We can try and increase the number of working hours per day. Now, when we get to 24, we got a problem with that one. And the favorite of the pointy-haired boss, use cheaper people. Now, of course, some of these things are silly. In parallelizing to shrink critical paths, here's an example, of course, where we're going to do 2 and 3 in parallel together, and this assumes we've got the resources to do this, and now we can actually get all those done. In a PERT diagram, we can also nest these things. In fact, with a complicated PERT diagram, which literally may have thousands of nodes, you can't look at 1,000 nodes at a time. But here we've got, for example, activity C, which is fairly complicated, blowing up. And here, coming in from A, we go into this whole thing, which is activity C. And you can see the complexity of activity C, which would blow up when we're actually doing C. And then we shrink it down again when we get C out of the way, and we go on to look at something else. The PERT life cycle are basically to lay out the list of activities, order them sequentially according to the activity definition, add the arrows, check with the line managers to make sure we've got people available at that time to do it. Then the people that are going to actually do the work have to plug in their time estimates, and again, we're assuming unlimited resources. The project manager has to add in calendar dates and things like not working on the weekends and high holidays, that sort of thing. And then we want to make sure that they're reasonable. Now, the nice thing about PERT diagrams is that we want to check to make sure if times change dramatically, what will the schedule look like? And so some of the objectives we can play around with, and we call this a perturbation analysis. What is the jigging of the schedule that will give us the best time to completion? What is the least cost for completion? What is the least risk for completion? Other secondary objectives in the handling perturbation analysis are basically taking a look at the consequences of alternatives, trying to optimize the schedule on some basis to effectively reuse resources, and so on. Constraints on the PERT diagram are things like the calendar completion, the flow of cash to make sure we have enough money. What if we have limited resources? What if we have to get management approvals for certain aspects? Now, in general, when we compare PERTs against critical path methods, critical paths do not have any ambiguity. Every activity has a fixed length for completion. The PERT diagram, they have a standard deviation. So they basically are event-oriented, and they're good for things like research and development, areas where we can't tell the actual completion time because of the complexity of the work we're doing, and we can't tell the percentage complete of any activity when we're executing it. And typically we'll get payouts, for example, at milestones rather than day-to-day activities. Critical paths are basically activity-oriented, and this is great for extremely well-defined activities, where you can measure the percentage complete along the lines of a Gantt chart. For example, you know you're 37% complete because if you're doing something like digging an excavation, you know how many cubic meters of soil you can dig out per day. And again, critical paths are best for well-defined projects for a dominant organization with small risk and one geographic location. And of course, PERTs are best for the ones that don't satisfy those categories. Okay, now organizations are going to have general templates we can work with, and then if portions of the work are repetitive, like building a skyscraper, you build a floor at a time, boink, 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 boink. So on things like that, we can actually generate the critical path fairly simply. The dependency determination we've already mentioned, mandatory dependencies, discretionary dependencies where we have a different paths that we can execute, external dependencies like the deliverable of hardware or outsourced pieces of the work, etc. And then internal dependencies say you can't test the code before you write the code, for example. And finally, we need to talk a little bit about leads and lags. Leads and lags basically allow us to accelerate or deaccelerate the start date of the successor task. So for example, I can start writing chapter 2 15 days before chapter 1 is completed. If that's completed, then I've got a finish to start relationship here, where I've got a 15-day lead. I can start the actual downstream relationship 15 days before this guy is scheduled to complete. Lags are the reverse. They delay the downstream task. So for example, concrete has to cure after I lay the concrete, then I've got a lag of 15 days. So I've got a finish to start relationship here, which means when I finish this activity, pouring the concrete, I must wait 15 days before I can start the downstream activity. And leads and lags can be negative too. They don't always have to be positive. So if B lags A by 3, for example, when I actually complete A after 4 units here, I have to wait 3 more lag units before I can start on day 8 at that particular time. Finally, the output for this activity is going to be the project schedule network. It's going to look something like this, so we get the thing completed. And this is now going to likely be blown up into a big giant diagram for all to see.